Thanks, Renzo. Apologies, we're all a little bit sick. Um, so I'm trying to show you today what we kind of like have got working. There's, still a lot of work in progress, and not everything is kind of like solved. Um, Also, please, I don't have too much material. Please feel free to jump in and ask questions. Just raise your hands. I have the Zoom window, so that I should be able to see it, or Renzo can remind me. And yeah, so basically, this will not just be fMRI, because as I try to, like show you in the title that, we have people who want to do neuroscience, and that includes also a lot of structural imaging. So I start with, like structural imaging, and then I show you a little bit of what we've done on the functional side. And um, most of you know the system, but those who are not kind of like familiar with it, so we have the next gen or Terra.X Impulse system. And yeah, field strength is 70. So we are currently on the software baseline XB10, which is a little bit of a unicorn. I think us in Magdeburg and some PET MRIs are kind of like the only ones who have it. I don't know, Renzo, what you will get. Um, but which kind of like, comes with its own challenges, actually. And the special thing, or one of the special things about the system, is obviously the gradient system, which, David Feinberg initially developed together with Siemens. They call it kind of like the next gen, or the branding is now the impulse system. And what the aim was to have a system with, kind of like a really, really high maximum gradient strength of 200 millitesla per meter. If you have like a standard Terra, you get about 80 millitesla per meter. And also have like a really, really high slew rate of 900 millitesla per meter, which is kind of like in standard system around 200 millitesla per meter. Another factor is kind of like the ADC sampling rate, which is 2 megahertz, which basically kind of like, kind of tells you or determines what's, together with your field of view, what's the kind of like maximum G max you can resolve. So you can see, if you take into account like a field of view of 200 millimeter over sampling factor of 2, and you can kind of like solve of the G max. And so with our ADCs at the moment, we can sample at 117 millitesla per meter. So that's kind of like the maximum gradient strength we could resolve. Which means we are not kind of like, cannot use the full 200 millitesla per meter. But of course, you can use those for example, motion encoding, flow encoding, and of course, diffusion. The head coil we use is an 8-channel transmit, 63-channel receive, built by Shajan. And basically, the sequences that are available at the system at the moment are mostly product sequences. So we obviously have an MP2H, we have a GRE, we have a T2 space, 2D bold, TOF, which is kind of like a derivative of the beat. In past implementation, or the past system was kind of like its own sequence. Now it's kind of like derived from this kind of like massive sequence block. There are unfortunately no whips so far. We have been promised, oh, that's true. The 3D API is also a product. Yeah, and I'm kind of like the ones that are highlighted, I'll talk about, and the others I won't. Um, Unfortunately, I know whip, so we're supposed to get the B0 shim tool from Ali. Also the 3D API to do a little bit more digging into the product version, and the T2 space with universal pulses are also, or with, what was it? Yeah, something with the G2 space is also supposed to come. And there are also only 2 C2P packages at the moment, which is the 3D API from Rüdiger Stirnberg and the CMRR 2D API. And that's, I think, a little bit the challenge with the system at the moment, that there's not too much available in terms of sequences and C2Ps. So yeah, as I said, I'm going to show you a lot of anatomical imaging because that's what we've been kind of like focusing on a little bit at the moment. So MP2 rate is kind of like kind of like the workhorse. Um, People kind of like usually like 0.7 millimeter isotropic resolution. So I've kind of like moved from VE12U to kind of like XB10. And in the VE12U system, if people remember, basically, kind of like PTX and, single transmit were kind of like two separate systems. Now everything is kind of like merged into one, and you're kind of like always on a, PTX capable system. You can still kind of like operate it and, kind of like single transmit. Well, it's not single transmit, but kind of like no B1 shimming or no PTX pulses required. So you can call it operate it in CP mode, so circular polarized. Siemens calls it true form, or you can do B1 shimming, which is kind of like enabled by the sequence, which is kind of like it's not kind of like full PTX, but it tries to homogenize I think the amplitudes. Um, and they call it kind of like patient specific. Um, so this is kind of like one of the protocols we use, which kind of like gave, reasonable images. Um, and you can see, so the first thing that we really noticed with this system is that how big the gradient nonlinearities were. So this is basically the non-corrected version, and here you can see the corrected version. And I find it, I mean, I admit I've never done this kind of like conscious comparison previously on like a normal gradient system, but I was just blown away, kind of like how, everything in that brain basically moves around due to gradient nonlinearities. Um, Obviously, you want to correct them, maybe not as the first step in your pipeline, but it's just, something to be really, really conscious about, that if you take any kind of measurements in terms of cortical thickness or what else from this system, that you need to take into account, kind of like the gradient nonlinearities. I think the corpus callosum is kind of like the only thing that stays in place, and everything, gets shifted around. Um, we did, a traveling head study together with Magdeburg. So I'm showing you the data from Magdeburg and Stanford because we are, kind of like identical baselines. Henrik Matton has visited us, and so I'm, showing you kind of like the cross correlation between different sessions, using kind of like a rigid registration and brain mass, and you can say, see, kind of like we actually have pretty high cross correlation, so that's good. The system, reproducibly gives you the same images. So the first three sessions are Stanford, and the last four sessions are Magdeburg. Session one was basically a test session for both of them. And Magdeburg in this first session, I could talk about it again, but so you don't have a laser. Oopsie. So the table just, kind of like goes all the way in, and you basically have to put your coil somewhere on that table and hope it's an isocenter. And the first time, kind of like Magdeburg did their measurement, they can like put it in kind of like a slightly different position because their coil is, I think, 1 or 2 centimeters longer than ours. And you can see that, these 2 centimeters offset mean that the images look very, very different. But if we perform nonlinear registration, then suddenly everything kind of like becomes the same. So yeah, I just wanted to, show you that you get, very, very reproducible images out of the scanner, but details matter. So this kind of like, gradient nonlinearity is really a huge effect. And I will talk about the position again for the EPIs. And you can see here, just as a comparison, this is just from I think B0 B1 map, which is basically a gray blob, the cross correlation. So this is kind of like really, really high and nice values. Then we compared the CP mode with the B1 shim, which, as I said, it's not yet PTX for the MP2 rate. And you can see that, there are some differences, but they're kind of like not huge. So the, kind of like median absolute difference is around 8%. But on average, they're kind of like the same. You can see, kind of like some intensity, kind of like variations, but are kind of like pretty broad across the brain and obviously a little bit, on tissue interfaces. So it helps a little bit, but it's, kind of like not straightforward to say that one or the other is better.
Could I,
However,
yeah.
yeah.
Sorry, could I ask something about the comment that this is not PTX yet? Like you mentioned this with respect to the VIP of the T2, I guess maybe. So the product sequence of the MP Rage does have the focus pulses in there, right? And so that there is like PTL's pulse design from XA60. Are you saying that with the Shajan coil, I guess because the eight elements are different than the Nova coil, you don't have that capability in the product? Or like,
Um,
can you use
no, I think
PTX pulse
yes,
design on the
so I
MP
think
Rage?
we can use it. Um, Let me remember.
I could
Yeah,
probably
everything.
a little bit. So, I mean, every transmit coil will need a library of B0 and B1 maps, B1 plus maps, in order to create universal pulses, which are the starting point for a lot of the patient-specific focus pulses. So until you have that library, and that library is collected at high resolution, so not with the standard Siemens B0 and B1 mapping, you need higher resolution. You won't ever see a benefit in the PTX or dynamic PTX. So that's something that Stanford and you guys and whoever else using Shahjahan's coil are going to have to build, basically.
Yeah. So yeah, I'm trying to remember if, kind of like we tried it and it didn't look good or we haven't but I think like people tried it and was, a little bit nah, because, it uses the kind of like B1 measurements, kind of like from within Siemens, which are really, really fast, but not, very high resolution. I show you a T2 space that Omer, set up with kind of like proper PTX, which looks pretty good. So I think it's, yeah, just so it kind of like the B1 streaming, you just kind of like click it and well, that's not true either because Omer had to kind of like change the algorithm that
Yeah,
it
you have to
used.
use a block Siegert, and you have because that's not sensitive, or you can make it non-sensitive to respiration. Otherwise, the B naught doesn't come out so great. Omer developed all of that while he was here.
Exactly.
We know it works beautifully. So all you have to do, you just have to map 20, 30 people, and then you're ready to go.
Yeah. Yeah. So I think we have now maybe 12 or 15 or so. Um, and we can like hope that, that was kind of like part of the study as well, that we can kind of like pool together with Magdeburg. So, and maybe with you guys as well, to, kind of like, have like one set of universal pulses for all three coils, although they might be kind of like slightly different. Yeah. So yeah, I think like it's possible it either didn't do much or it didn't work very well. So people at the moment can like stay either with just true form or patient specific. I mean, it also, can like obviously takes time to like do the B1 map, do the calculations and everything. And we had a couple of catastrophic failures where there's basically like, a black hole in the middle of the brain. And that's due to the, like algorithm that was used. There's like a fast version that Siemens liked because if you do kind of like slice by slice shimming, then obviously you don't want to wait 3 seconds per slice or whatever it takes. But if you do kind of like 3D imaging, then obviously 3 seconds for that algorithm to compute is totally fine. So that was one of the things that we had to kind of like change. So kind of like technically we're not using like the product, but product system or product sequence that Omer has kind of like slightly tweaked for us. Another problem was that the interface was kind of like really, really slow. And that was because there was kind of like 100 print statements somewhere in the code. So that was another thing that Omer kind of like fixed for us to actually make it, workable and usable. Yeah, but I'm yeah, kind of like, now we have, at least a system to get, some more decent MP2 range images. Yeah, and like the GRE, I think, yeah, the MP2H, it's just something that we need. The GRE just, like, I think is one of the first examples, although I haven't, compared it to like a standard system where you can fairly comfortably use, like the gradient performance and get like really, really short TEs because we are interested in, characterizing some short T2 star species. And yeah, this is just like an example image. And yeah, like the nice thing is obviously like with, like these short TEs and TRs, you can also, basically get like a whole brain coverage in, 6 minutes. Yeah, and that's the T2 space that I was talking about. So this is now with PTX, with basically some magic from Omer to so he uses, as Ravi mentioned, like Bloch-Ziegert-Shift V1 map, and based on that, then computes the PTX pulses. And you can see that I was like really impressed about the detail, like in subcortical structures and the cerebellum, how like nice and homogeneous all of this comes out. If you look really, really closely and like around motor cortex, you can see that the gray matter white matter contrast is kind of like a little bit fizzling out there. But overall, I think this is kind of like a really, really, really nice T2 image on 7T. And yeah, I've been kind of like starting to work on, as Francis said, high resolution vascular imaging. I was initially excited about the, kind of like compressed sensing that's available on the system. But unfortunately, my experience, the protocols I set up, they always crash the recon. So I have, for now, given up on that. So we are back to, normal grappa. And here I kind of like try to, kind of like slightly different philosophy because eventually we want to have, kind of like whole brain coverage. And for that, we don't want to take ages. So kind of like, the usual philosophy of like flow compensation, whatever, venous saturation, long TRs, high flip angles, that always, kind of like goes against large coverage and high resolution. So what we've done here is basically threw that all out, minimized our TE, which, there's no flow compensation here. And my argument is, what's going to happen in 1.6 milliseconds? Minimize the TR to obviously get a lot of coverage. The flip angle, like is, obviously still high, but not as high as you like would usually use. And kind of like acquisition time is, under 4 minutes. So it's not kind of like too much of a problem to kind of like do multiple slaps of that without the participant moving too much. This is kind of like the maximum I can kind of like do at the moment because, or you're kind of like running into limits in terms of matrix size. So we need to go in and kind of like increase the maximum matrix size to go to kind of like lower resolution, or higher resolution, lower voxel size. But I think that's kind of like a really, really neat approach because getting, kind of like whole brain images at high resolution was always something that I struggled with. And I think that makes it now more feasible, kind of like to include that in studies where we maybe had like a, dedicated vascular imaging session. And yes, so now we're kind of like slowly moving towards EPI. So this is the 3D EPI from Rüdi Stirnberg, from the Deutsches Zentrum for German Center for Neurodegenerative Diseases. So this is a kind of like comes from the kind of like Hertz study. This is a single echo, 0.4 millimeter isotropic, takes about 5 minutes. And I think we are kind of like, or one of our collaborators is interested in QSM. That's why I'm always like showing QSM whenever there's a T2 star. I think the original protocol takes maybe 6 minutes, or maybe but it's kind of like also required in a slightly different orientation. So it's a little bit of an apples and orange comparison. But I think it just shows that you get really, really, really nice images with the 3D API on the system. And these are two images averaged. So they're both acquired. They both take like 2.5 minutes to acquire using dual polarity. So you can get rid of some of the, like fuzzy ripple artifacts. And the next one is my kind of like absolute favorite. So if you are familiar with Farouk's work, you can like know of the, like mesovein imaging. And here I, like basically just put in the same parameters, same acceleration, same field of view, same matrix size, same everything. And then all I did was, like crank up the bandwidth to the maximum it would go. And it basically gave me twice as many echoes. So instead of 3 echoes, we now get 6 in exactly the same acquisition time. And that's, just comes out from the gradient system itself. And the shortest echo time is 5 milliseconds. So again, you can, start looking at some of kind of like shorter TE species. And I think, which quality-wise, you couldn't tell it apart from a GRE, I think. Or maybe you can because it looks better. So this is an average over the 3 runs. They, like each takes about 7 minutes. And yeah, it's just something I'm very excited about. And yeah, so functional imaging. This is so basically PNS has really, really challenged us on the system. Also because it is a bit counterintuitive sometimes. But in case you're not aware, so one of the, kind of like considerations in the design of the gradient coil was actually the peripheral nerve stimulation. And here you can see like 3, kind of like theoretical drafts where they kind of like included PNS balancing, and then also where they, kind of like introduced this mid layer, which is kind of like a new, kind of like the new feature of that coil. And you can see how, kind of like introduces the B fields, and that also kind of like reduces the E fields, and that, kind of like also reduces kind of like, the intensity of the PNS, at least in theory. So this is basically performance metrics from, the simulation and also experiments performed in Erlangen. And the gray region is kind of like the operational region, and it tells you what kind of like the, mechanical or electric, well, kind of like theoretical capabilities of the system it could run at. And the red region is then basically, kind of like the limits due to PNS. And you can see that, it's pretty promising. You're obviously losing a little bit of the operational region, but overall you can, kind of like more or less make, good or pretty much use a lot of the system's kind of like technical capabilities. However, this later on didn't quite match up with the experiences in Berkeley. So I only need you to, kind of like focus on the blue and the red lines. So the red lines are basically the measurements from Erlangen, so the Siemens factory, and the blue lines are the measurements in Berkeley. And you can see that the blue curve, especially on X, is much, 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 much lower than what was measured in Erlangen. We still don't know why this is the case, but overall, our experiences are probably closer to Berkeley as well. One interesting finding that we did by chance together with Renzo, and that, eventually we saw also reported in a paper, was that if you come like further out in Z, so further out of the coil, so don't put your patients or like participant all the way into isocenter, you can like reduce the PNS quite a bit, which was helpful for a while for us to connect scan. But the newest, yeah, so our experience with this. So question number one, as I said, where is the isocenter? Because we don't have a laser, the table just goes all the way in. And when I scanned the first time on the system, I did what I always did. I just shoved the coil all the way it would go to the very end of the bed. And we had terrible PNS. Like people squeeze the squeeze ball all the time. So then in a discussion with Omer, I realized he's like, oh, no, you're not putting the coil in isocenter. So you have to kind of like leave a little gap. And we now have printed a spacer, and Magdeburg also has a spacer to basically, leave about, I would say, 2 centimeters between the, kind of like top of the table and, the top of your coil to kind of like move the coil into isocenter. So that was kind of like the first thing, we learned that, yeah, you have to know where isocenter is now. And this is from a project together with Kalanit and Seda and her team. So these are example protocols. So they want to basically say, you have 1 second TR, what can you give us in, kind of like whole cerebrum coverage? So we set up a couple of sequences for them at 0.8, 0.4, and 1 millimeter. What I find pretty cool is that, at 1.8, you don't even need grappa. You can just, read fully in, read out fully, like in, sorry, just give me 1 second to blow my nose. So you can, read out the case-based plane fully without any requirements for grappa. And you also only use kind of like multiband to basically get down the TR to 1 second. So that kind of like gave us medium PNS. And PNS in that system feels kind of like different. So people are, it's more like a pressure feeling. It's not like, the classical tingling, what is usually prescribed. And it's all usually on the face, sometimes the neck. I think I had like 1 person in the shoulder. So it's kind of like definitely different. So you want to, prime, or maybe not your participant that, it's not the classical PNS feeling, but it can be like a pressure or something that many people describe. Yeah, so at 1.4, you need a little bit of grappa and a little bit of SMS, and kind of like obviously at 1 millimeter, you need more SMS just to kind of like get down in terms of TR. Interestingly, kind of like the 1.4 gave us the least issues. And the 1 millimeter was really the one where people, squeezed the squeeze ball and said, wow, this is really painful. But yeah, we're just kind of like, yeah, also, yeah, a problem. So the first thing we did, we moved kind of like the participants out of isocenter, which helped a lot. So then, kind of like the still setup, we feel a little bit, but it's a lot better than what it was before. And recently, we changed the gradient mode to normal. And, people report either no PNS or a little bit of tingling during the reference lines, and then it's gone. We kind of like are looking into this. It's like the opposite of what you would expect from the simulations, because normal gradient mode gives you actually higher, kind of like amplitude, because the, like slopes are, yes, the slopes are, less steep. So I think you need higher amplitude. Yeah, so it's kind of like, the PNS model would tell you normal is worse than fast. but in our experience, it's kind of like the exact opposite. We're still investigating. I can't, tell you why this is the case, but it's, keeping us plenty busy. And yeah, and now, so Omar was really nice, and he basically added a little drop-down menu, so now we can turn our impulse into a normal SC72. First, yeah, images first. So this is kind of like the, images you get out of that. So I think kind of like the 1.8 looks really nice. Oh, one thing I forgot. So these all come with ghost reduction, it's called. It's basically the Siemens implementation of dual polarity grappa. And that needs to be on. Otherwise, you always have ghosts. So that's doesn't cost you anything, but Renzo.
And that's the case also when you don't do any grappa, or like only some grappa.
No, sorry, obviously not for the 1.8. Yes, if you don't do grappa, then you don't need it. But the moment you turn on grappa, I think like for the fairly, let me try to remember. It wasn't too bad for like the low resolution, but I think at 1.5, 1.4, it really. Yeah, it really makes a big difference for us. Yeah.
Thanks.
Yeah, and yeah, you can see kind of like obviously at 1 millimeter, the wheels are slowly coming off. There are quite a few artifacts, and I'll show you one more that maybe some of you have some ideas for. But overall, kind of like pretty nice images, especially given the constraint of 1 second. Yeah, and then Omar kind of like
were those TSNR maps on the bottom?
Oh, yes, that's TSNR. Sorry, yes, that's TSNR. So you can, obviously kind of see we follow physics. But yeah, I don't know. I'm a bit partial to that 1.4 millimeter protocol. I think it's pretty nice. I don't know, 1 millimeter in 1 second obviously sounds cooler. But yeah, that yeah. And yes, as I was saying, Omar put a little button in there, a little drop down, to turn it back into an SC72. And this is, kind of like obviously just a fun exercise, but what would happen if you had, like the normal settings? And you can see that, obviously you'll probably, have a pretty, obviously the TE goes up because the bandwidth goes down quite a bit, and the echo spacing goes up, and the TR goes up. So I would take like, on average, you get about 50% increase in TE and TR if you were on a normal system, which makes I think like especially the 1 millimeter protocol just not usable anymore. But I think that's because we don't have kind of like a normal system, so it's always a little bit difficult for us to say, oh, this is like better or worse or different. So I made this as a little toy example just to kind of get a feeling of where we are in terms of capabilities. And yeah, the artifact. So this is kind of like the current artifact that we are looking at. I looked back at the data, I felt like it was faintly there always, but now it's gotten really, really bad. Another group also independently stumbled into that, so it's not just me. So this is basically the 1 millimeter. Due to kind of like the other artifacts, we decided to back off a little bit in terms of multiband. So this is now 2 second TR. Also, they wanted more coverage, especially around the temporal lobe, so we increased the slice coverage a bit. It also shows up in the phantom. So in the beginning, we thought, oh, this is maybe motion during the reference lines because they take long. It's like 1 minute of just reference lines. But it's less strong, but still there in a phantom as well, which doesn't move. So yeah, any ideas?
Hey, Saskia, can you point out Can I just make sure I understand where exactly is the artifact you're talking about? Is that
Oh,
the stripes?
yes, exactly. Kind of like these stripy lines. So those are basically, like slice to slice intensity variations.
Okay.
Which
Okay.
which reference do you use, Saskia? Like which reference acquisition?
I think it's in this one, EPI separate. We also tried it with Fleet. It helps a little bit, but it's not like, it doesn't really solve it.
Hey Saskia, it's Joseph. Can you hear me?
Yes, I can hear you.
So this sounds familiar to me for what we're doing with diffusion, going to thinner slices, and with multiband. This is the CMR sequence, is that correct?
No, this is the product.
Product, like Siemens product,
Yes.
2D.
Yes.
It might have the similar behavior. You could try slightly different slices and double check the slice timing, because when you have multi-band, the number of shots can change the slice order so that adjacent slices get excited much more quickly than what you normally expect for an interleave slice order. That might be causing it. So it's interesting that the slice order with multi-band, it can change depending, just a slight tweak to the number of slices. So that would be something to check if that's the case. And if you plot the slice timing for each of the slices, for those different cases, for different number of slices, you should see the change, and that you're not exciting adjacent slices right after the other. So just try that and see if it helps.
Okay, yeah, that's a great advice. Thank
There
you.
is a bug in the CMRR code, which may also be there in the Siemens SMS code, which is if the number of slices in the Z direction, well, any direction in the is not a multiple of the SMS value, you get weird things like this. So you might want to check that as well. It's related to what Joseph was talking about, but you actually need a multiple of the slices. Otherwise, the slice timing gets all goofed up.
Okay, cool. Thank you. Yeah, I didn't consider that. I was kind of like suspicious of multiband, but then I was like, oh, it's like alternating slices, which doesn't really match the multiband factor. So
Comment there.
yeah, okay, cool. Thank you so much. Um, yeah, and this is kind of like CoBrain API, this time using, kind of like the 3D implementation from Rudy. Rancer developed a protocol. Resolution was 0.85 isotropic. Like, pretty intense acceleration, so a little bit more than what we did for the 2D. But yeah, I think like the images look really, really nice. And I just like in the TSNR maps, thresholded them a little like differently. So, but overall, I would say they look, not worse than, like the 1 millimeter. Obviously although the TR, oh yeah, the TR is also 2 seconds, so they're actually comparable. So I think that's, a really, really kind of like nice protocol to run on this system. And I think it's, yeah, Renzo can say more to that, but you said this is not possible kind of like on standard systems because you can't jump to the higher bandwidth, right?
Correct. Yes, I think this protocol might have been adapted from stuff that Alex Beckett did, like for the readout for the VASO that we did on the Feinberg system. And I think that the really critical thing that you cannot do on the conventional Terra is that you jump on the other side of the forbidden frequencies. Like you wouldn't get echo spacings of 0.6, right? You're always stuck against, and you run until like against this, yeah, invisible wall of the 1 millisecond echo spacing with these kind of resolutions. And with that system, you can really like have neuroscience applicable TRs of 2 seconds, and you're not stuck with the kind of 3-4 second regime. Yeah. Yeah, it looks great. Thanks for sharing this.
Yeah. And yeah, kind of like that's it. So I want to kind of like just acknowledge a couple of people, especially Doug, Maddie, Omar, Brian, Adam, Michael, and Reese, who kind of have been kind of like working really hard on the technical side of things. So this is not all work I have done. This was done by a lot of people who have come together and really try to solve a lot of issues, understand the new system. Also, thanks to Seda and Kalani, who are really driving our 2D EPI efforts and really challenge us to kind of like see what the system can do. And yeah, let me know if you have any questions or any kind of like other ideas.
Thanks. Thanks a lot for this nice overview. It's very exciting. And the images are really beautiful.
Yeah, I mean, I obviously also have images that are not beautiful, but I wanted to show what works.
Maybe I have a question of, I guess, participant handling. What about your biggest surprises? Or maybe you handled this or touched upon this with respect to the PNS as well. And maybe do you have any surprises with respect to acoustic, sound pressure, or let's say with maybe the size of the person, like that the gradient is built for a given size human, right? You need to have a certain neck length, and if you are like if you think about neuroscience application, people might think about pediatrics, right? And then the neck is shorter, so your head doesn't even fit into isocenter. Did you ever consider that, or is there a limit actually for the impulse that you cannot scan people below a certain like length or something like that? Anything surprising?
I mean, kind of like I would say, kind of like on the other side, people with really large heads don't fit into the coil. So I mean, really large is like, normal males with a little bit bigger heads. So I had a couple of like issues where I had to, use really, really thin padding to kind of like fit them in. So I would say kind of like in terms of limits, that is more the case. I mean, in terms of neck length, yeah, I mean, it is a weird thing. I don't know if people like know how it looks like. I should maybe have brought a picture, but basically you have at the top of the table, you have like, little plastic thingies that sit on your shoulders. And that kind of like limit how far you can go in. And then kind of like the coil is here. So people have to sometimes stretch themselves a little bit to fit in. Obviously you can, move around the coil a little bit. So then you might not be at perfectly nice center, but you can probably make it fit. What we are now working on is kind of like the mirror setup. So it's pretty tight. So the mirror at the moment only slides, but people with very small heads who are lower then don't see a lot because you have to be kind of like pretty much at the kind of like top of the coil for the mirror to work well. So this is not a kind of like limiting factor, but this is just be aware that you probably want to kind of like manufacture a little hinge or something for the coil mirror. The other thing is, there are some people who are just like, no, I don't go in. This is too tight. They just look at it and say, no, I won't do it. Everybody who has been inside was either like, yeah, whatever, fine, or, oh, this was actually really comfortable. You're very snug. So everything is very tight. Not like, unpleasantly tight, but, very snug. And yeah, sound, I was a bit worried, to be honest, from my kind of like, 1 day or 2 day experiences in Magdeburg a few years back. But, we give ear protection and we put a lot of or as much padding as we can. And people have not like complained about it. I mean, it's, it's loud, but no one was like, no, it's, I won't do it or anything. So yeah, it's yeah, patient handling has actually, except, for the whole PNS story, has been surprisingly good.
Cool. Thanks.
Yeah. Yeah. And yeah, I mean the system has its quirks, obviously. But you will learn about them.
I do have more questions, but maybe I want to give other people's the chance to ask as well.
Can I ask a couple of questions? Hey, Saskia, thanks for the presentation. There's a lot of information to process. I want to ask, what is the typical slew rate for your 3D EPI and 2D EPI protocols?
Ooh, that's a very good question that I unfortunately can't answer right now. We just
Okay,
Yeah, but
that's fine.
we just actually like, opened up the 2D API a little bit and now, like added like a little, text box on a special card. Maddie did that for us so we can, look at these parameters because yes, we also want to know.
Okay. So do you think you're anywhere close to that 900 slew rate limit?
I honestly can't tell you, but
Okay. Okay. I was just wondering, with that spec, is that a single axis slew rate limit or is it combined all three axes?
I think that's single axis.
Single axis. But the G max is combined. Is that or is it also single axis? The 200
My guess would also be single axis.
single axis. Okay.
Or combine. Oh, yeah, I see you. Oh,
No, I would think it would be single axis. I mean, we have an AC84, and that is 80 millitesla maximum per axis, slew rate 400. Given the amplifiers for the impulse and everything, it has to be 200 per axis.
Okay. So both G max and the slew rate are for single axis.
I would think
Okay.
so.
Okay, great. Another question is when you mentioned the gradient linearity correction for the MP range, is that a feature of the product
yes.
MP range sequence? Okay, so then your suggestion is to always leave it on the
Well, I mean, the problem
correction.
is, like you acquire your nice high resolution images. Like the first thing you do is interpolate them, right?
Okay.
So from a, like processing perspective, it's not ideal. So what you would rather do is have these parameters, like estimate all your transformation into M&I space, whatever, and, add them because in the end you want to preserve resolution and you preserve resolution by only interpolating ones in your like whole processing pipeline. So ideally you want to like do that in post-processing and combine it with your normalization and whatever. Combine it with whatever else processing you do on the image. It also does some really weird stuff to like the intensity values. I mean, it's not so bad on the image, but let me see if you can see it. You can like introduce. Let me yeah so, yeah. Do you see like this stuff at the top, like these
Yeah.
white stripes?
Yeah.
Yeah, I don't know why they are there, but they can like somehow become very prominent when you turn on gradient. And also can like the denoising, can like to get the like uniden images, you can like set a number for the threshold. But that number, I think, so I did this now all offline. Works either for the, so you need kind of like different values for the, distortion corrected and non-distortion corrected images for some reason.
Okay. And the gradient is nonlinear. Is it in the sense that the K space is not exactly where you would expect based on the gradient values?
Well, it's basically, kind of like you assume that, kind of like that, kind of like the gradient amplitude, kind of like increases linearly across space, but it instead is kind of like, more like a like slope towards, more like, kind of like, and then it kind of like fades off.
So the K space value is not exactly where you would expect So the okay, so the gradient, so it's basically a gradient fidelity problem, I would think.
Yeah, I mean, you have a gradient coil that's not much bigger than the head, so it is highly nonlinear after you get out from the central part of the brain. And it's worse in the Z
Ah,
direction.
okay. So
So
you're talking about the spatial nonlinearity.
Yes.
yeah, spatial
Okay. Oh, I
nonlinearity,
see. Okay.
not amplitude nonlinearity. I mean, that's
Okay.
that's the key. I mean, for our AC84, and it looks like this gradient has very similar coverage. I mean, you can't even do spin tagging because the field collapses at the neck. So,
Yeah.
if you image an axial image down there, it's just almost a point source. And that when you do correct, so we do distortion correction having used a high resolution phantom, and we do that straight off the scanner. It kind of violates the principle Saskia was mentioning of do correction only once, but for anatomics, that's what we do. For functionals, we do something different. So that's looks like it's an issue here too. So
Yeah, I mean, you can see, like how squished the neck is.
yeah, the cerebellum starts to become a little square, and then I mean you can see the carotids.
Yes.
So
Yeah. Okay.
but you can't see. I mean, you can see C2 maybe, which is all we can see also. And it depends. Like Omer had the biggest head in our group. So he was sort of the big outlier. He and Kyle Gilbert are the two big heads. And that was, you could almost tell from the distortion maps what was going on.
Okay. Thank you. Thank you, Saskia.
Thanks, Dylan.
Thank you.
Do we have another question?
Oh, wait, there's one in the chat.
Yeah. It's from Rob Frost. You can read it, right?
Yes, going back to the lower PNS with the normal gradient mode. Maybe I missed something, but doesn't using normal instead of fast reduce the slew rate, so it's expected that it reduces PNS. So maybe. So basically what like Maddie and Brian did, they kind of like used, or Maddie especially, he kind of like, used the PNS model from Siemens. And there is basically amplitude and slew rate in there. And it has kind of like a couple of second order effects as well. And at least, from that PNS model, normal is worse than fast, theoretically. But practically, we've seen the opposite. And also Brian, kind of like they used, kind of like their own model that they fitted to the Berkeley data. And there again, that aligns more with what we've seen empirically. So I think like the answer to your question is that probably the PNS model needs a little bit more fine tuning for that system. Okay. But yeah. We're still, investigating, and technically, obviously, we are not, I didn't plan to run a PNS study, so this is all a little bit anecdotal, and, we tried this and we tried that and just try to get around it. But I think, we need to, do a little bit more of a thorough comparison there.
Maybe I can ask another question. About the comparison with the SA72, like you compared the parameters, and I was wondering if you also compared like images as
No,
kind of.
no, I haven't acquired images. I mean, yes, I could do that, but okay. But then, I mean, obviously, like, I mean, we should do that, but I'm then also thinking, it's maybe not quite fair because obviously that gradient has, less nonlinearities and maybe, some other problems.
Right.
Or so I think like it would be fairer to then, also compare it to like the actual gradient.
Right.
I mean, this was just a toy example to show a little bit. Yes, where we are, what you get,
Right.
roughly. But yeah, like, for an actual comparison, I would, like to do it with, also the gradient itself and the coil and everything.
Makes sense. Yeah.
Yeah.
I guess it might also go the other way around that, kind of using the impulse gradient and kind of dialing it down to an SE72 might actually look better than the SE72, because kind of your the grading quality might be kind of more exact, right? The eddy current compensation, which includes shorter terms, might perform better, but also these regularizer ringing artifacts that you sometimes see when you push the SE72, or even just the mechanical resonances, right? When in this comparison study from Nicolas Bollon, when he dialed down the impulse gradient to something like SE72, or if you retrospectively scale it, then it looks much more flat than if you would run it on a SE72. So and I guess my question is, or would have been, if you would have done the comparison, whether the impulse scanner is also a higher quality scanner, or if it's just about the quantity when you want to push it a lot.
Yeah, I mean, you're right. It could go both ways, but I think you want to have, that extra data point in there, be like, okay, this is. Yeah. And then you, I don't know, maybe need to scale it by monetary value or something.
Right. All right, we are at the full hour. Thanks a lot. Wait, maybe we have another question. Or maybe that was sent to me personally. Sorry. I will respond to that later. Thanks a lot, Saskia. And we all meet again in 2 weeks for a presentation with Antonia Maßmann. Thanks a lot.
Thank you, Saskia.
Thank you. Bye. Du musst hier klicken.